Goals for this section, we're going to mathematically relate the wavelength and frequency of electromagnetic radiation and the speed of light, and recognize the relative wavelength or frequency of the various types of electromagnetic radiation. Back at the beginning of this class, we described atoms as consisting of protons, neutrons, and electrons. The protons and neutrons are located in a small, very dense nucleus, and if you remember, the electrons occupy the space around the nucleus. In this chapter and the next one, we're going to explore the arrangement of electrons in atoms in more detail. Experiments on the interaction between atoms and the electromagnetic radiation were essential to developing theories of this electronic structure to atoms. So to understand these experiments, we first need to describe the features of electromagnetic radiation. Back in the 1800s, James Maxwell developed a mathematical theory to describe light and other forms of radiation in terms of oscillating or wave-like electric and magnetic fields. Visible light, microwaves, television, TV and radio waves, X-rays, and other forms of radiation are now called electromagnetic radiation. This is when atoms gain energy and they become excited. This added energy is absorbed by electrons and then released in the form of electromagnetic radiation. And as I was just saying, this electromagnetic radiation or light is composed of two orthogonal vectors, the electric wave and the magnetic wave. And we can see that they are perpendicular to each other. Here's a quick little video clip from our text.
Visible light is a form of electromagnetic radiation, which emanates from the source as waves. The waves are electric and magnetic fields oriented perpendicular to each other.
Now, electromagnetic radiation is characterized by its wavelength and frequency. The wavelength down here, this lambda, that's a Greek letter, is defined as the distance between a given point on a wave and the corresponding point in the next cycle of the wave. It's often measured as the distance between successive crests, or the high point of a wave, or between successive troughs, or the low point of the wave. And then we have frequency, so this is wavelength, and we typically measure it in nanometers. And then we have frequency, and that refers to the number of waves that pass a given point in a unit of time, usually per second. The unit for frequency, written either as S-1, which means inverse of seconds, or hertz. The wavelength and the frequency are related to the speed, this C, the speed of light. The speed of light is 2.998 times 10 to the 8th meters per second. That's a constant. That is the speed of visible light and all other forms of electromagnetic radiation in a vacuum. That's about 186,000 miles per second that light travels as. Now, does light travel as particles or waves? Well, we'll talk more about that later. Again, those units, if we look at the speed of light, that 2.998 is often rounded to 3.00, so 3 times 10 to the 8th meters per second, or it can be written meters seconds to the -1, which just means per second. Also meaning cycles per second, or hertz for our frequency. And then lambda is our distance, our wavelength. Radio waves can be measured in meters, visible light in nanometers. The intensity of light is a function of the wave's amplitude. The amplitude is the measure from this resting position to the crest, or the resting position to the trough. So we can see that there definitely is a greater frequency in this wave. So we can see that there's 1, 2, 3 crests in this amount of time, versus in the same amount of time, there's only 2 crests. The point of zero amplitude is called the node. Here's a picture of the whole electromagnetic spectrum. And as we can see, visible light is only a tiny portion of the total spectrum. UV, or ultraviolet radiation, is the radiation that can lead to sunburn, which is right here. We can see that it has wavelengths that are shorter than those of visible light. X-rays and gamma rays, the latter emitted in the process of the radioactive disintegration of some atoms, have even shorter wavelengths. So we can see even shorter as we go to the left. At wavelengths longer than visible light, so over here to the right, we first encounter infrared radiation, or IR. The wavelengths of the radiation used in microwave ovens, in television and radio transmissions, in MRI instruments, and cell phones are even longer. Let's look at an example problem here. The frequency of the radiation used in cell phones covers a range from about 800 megahertz to 2 gigahertz. So what is the wavelength in meters of a cell phone signal operating at 1.2 gigahertz? So we're going to use the equation of speed equals wavelength times frequency. What is the wavelength? So we want to solve for lambda, so we're going to divide both sides by v. So we know c is always the speed of light, 2.998 times 10 to the 8 meters per second, and we're going to be dividing by v, which is 1.2 gigahertz, 1.12 times 10 to the 9th, or we can say 1 over 6. So on your calculator, you're going to do 2.998 E8, which is times 10 to the 8th, divided by 1.12 E9, or times 10 to the 9th, you should get 0.268 meters. And if we look at 0.268 meters and where that falls, it's in the microwave region of the electromagnetic spectrum. Make sure you pay attention to units when we're solving this problem, because we need our wavelength to be in meters when we're looking at our spectrum here. How about this example problem? What's the wavelength of the radio waves from WOXY radio station? 97.9 megahertz. So we're given the frequency in mega. Remember, mega means 10 to the 6th. You know what the speed of light is, 2.998 times 10 to the 8th. Let's pause and try to work this one out. The wavelength is equal to c, speed of light, over v, and we get 3.06 meters. If we go back and look at our electromagnetic spectrum, 3.06 would be right here between this 10 to the 0 and 10 to the 1. So it would be our FM radio waves. Why don't you try a few more examples here, and then we'll go over them in just a minute. Which color in the visible spectrum has the highest frequency, and which has the lowest frequency? Is the wavelength of the radiation used in a microwave oven, which is given to you 2.45 gigahertz, longer or shorter than that from your favorite FM radio station, like, let's just say 91.7 or 103.3 or something like that, megahertz? Are the wavelengths of X-rays longer or shorter than those of ultraviolet light? And calculate the frequency of green light that has a wavelength of 510 nanometers. Try those and we'll go over the answers in just a second. So for that first question, which color in the visible spectrum has the highest frequency? Our highest frequency, we can see, is the energy increases would be my violet. And the lowest frequency will be my red. The second question, the wavelength of the radiation used in a microwave oven is shorter than that in the FM radio wavelength. Letter C, are the wavelengths of X-rays longer or shorter than UV light? They are also shorter. And to find the frequency of green light when we're given the wavelength, so we're going to do, remember, speed is equal to wavelength, my lambda, times frequency. So we're going to find the frequency, we're going to divide both sides by wavelength. 2.998 times 10 to the 8 meters per second divided by nanometers. So we need to convert that into meters, which is to the negative 9th. So 510 times 10 to the negative 9 meters. So if we do this in our calculator here, let's see what we get. And plugging that in, check with me though, you should get 5.88 times 10 to the 14th. And let's see, this is our frequency, so that's in hertz. How about this? Which of the following produces radiation of the highest frequency? So we had microwave, AM, FM radio, or red laser pointer. So if we look at this, we know that frequency and energy increases as we move to the left across the spectrum. We've got AM, we've got FM, we've got microwave, so our red laser pointer should be our answer. What about this one? Which of the following types of radiation has the longest wavelength? So if you look at the chart, you should see it's radio waves. We go back, longest, so as we go left, the frequency increases, so our wavelengths get shorter and shorter and closer together. If you think of this, as frequency increases, there are more waves per second, so the wavelength is getting smushed closer and closer together. And as we go to the right, we have longer wavelengths So wavelength increases, frequency decreases. What about this one? The local radio station has a frequency of 98.6 megahertz. What is the wavelength of the station in centimeters? Pause it, and we'll check in just a second. Hopefully you got 304 centimeters. Which of the type of radiation has the highest energy? Gamma rays. Calculate the frequency of orange light with a wavelength of 595 nanometers. You need to convert nanometers to meters. Hopefully you get 5.04 times 10 to the 14th hertz.
In this next section, we are going to look at the photoelectric effect and understand that the energy of a photon, a massless particle of radiation, is proportional to its frequency.
If you were told that you could drive your car at 23.4 miles per hour, or 28.9 miles per hour, or 34.2 miles per hour, but never any speed in between these values, you wouldn't believe it. You wouldn't be able to, would you? It sure would be interesting. Yeah, they discovered this about electrons in atoms.
Another example, imagine if you're walking up a flight of stairs. You can be on this step or you can be on this step, but you can't be in between steps. You can't be planted in between steps. Also think about climbing a ladder. You can be on one rung or you can climb up to the next rung, but you can't be in between. Or notes on a piano. You can be at C or you can be at C sharp, but there isn't an in-between note. You're at one note or another note. So Max Planck explained it by assuming that energy comes in these packets called quanta.
So what is quanta? Well, back in 1900, German physicist Max Planck proposed that light, heat, and other forms of radiation come in tiny bundles, which he called quanta. The amount of energy in a single particle, he said, depended on the frequency and can be given by the following equation. E equals hv, where v is the frequency, similar to when we did speed equals wavelength times frequency, and we used v, frequency of the wave, and h is a constant that came to be called Planck's constant. So this is looking at radiation given off by a heated body. And it shows us that at high temperatures, the maximum in the curve is the ultraviolet region. The object is described as white hot. As temperature of a heated object increases, the maximum in the curve moves from the red portion of the spectrum to the violet. We can see the red to the violet as it's heating. When it is heated, it is emitting radiation covering the spectrum of wavelengths. At the end of the 19th century, scientists were not able to explain the relationship between the intensity and the wavelength for radiation given off by a heated object. This is often called black body radiation. So theories available at the time predicted that as a solid is heated, the intensity should increase continuously with decreasing wavelength, instead of reaching a maximum and then declining as is actually observed. So this perplexing situation became known as the ultraviolet catastrophe because predictions failed in the ultraviolet region. Planck proposed that energy is quantized. Quantization means that only certain energies are allowed. The proportionality constant H, that is Planck's constant, is 6.63 times 10 to the negative fourth joules second. So the unit of frequency is 1 per second, or 1 over second. So the energy calculated using this equation is in joules. Energy is in joules. We remember just from this last chapter, Q equals m times c times delta t. Q is in joules. So if an oscillator changes from a higher energy to a lower one, energy is emitted as electromagnetic radiation. But the difference in energy between the higher and lower state was E equals delta N HV. And the value of delta N is 1, which corresponds to changing from one energy level to another. So then it was reduced. So having equal energy to energy equals HV. So here's the Planck's constant. And we say if it was 2 energy levels, it would be 2 HV. 3 energy levels, 3 HV. The key aspects of Planck's theory, important in general chemistry, are that Planck introduced the idea of quantized energies and the equation E equals HV, which is an equation that was to have an important impact on the work of Albert Einstein in explaining another phenomenon. We can look at Planck's law. We can say if energy is equal to HV, and we know that speed of light, c, was equal to wavelength times frequency. But if we rearrange that to solve for v as speed of light over wavelength, we could then say that energy is equal to h times speed of light over wavelength. As the frequency of light increases, the energy of the photon increases. As the wavelength of light increases, the energy of the photon decreases. So after Planck's work, Albert Einstein incorporated Planck's ideas into an explanation for the photoelectric effect. And in doing so, changed the description of electromagnetic radiation. In the photoelectric effect, electrons are ejected when light strikes the surface of a metal, but only if the frequency of the light is high enough. If light with a lower frequency is used, no electrons are ejected, regardless of the light's intensity or its brightness. If the frequency is at or above a minimum critical frequency, increasing the light intensity causes more electrons to be ejected. Here's a picture. Einstein decided that the experimental observations could be explained by combining Planck's equation with a new idea that light has particle-like properties. Einstein said that these massless particles, that he's going to be calling photons, as packets of energy. And he states that the energy of each photon is proportional to the frequency of the radiation as defined by Planck's constant. So in the photoelectric effect, photons striking atoms on a metal surface will cause electrons to be ejected only if the photons have enough energy. The greater number of photons that strike the surface at or above that threshold energy, the greater number of electrons are dislodged. The metal atoms will not lose electrons, however, if no individual photon has enough energy to dislodge an electron from the atom. And this just reiterates what we just said. There needs to be that minimum energy applied or no electrons will be observed. And the number of electrons ejected depends on the light intensity.
This is also just a nice visual to see the long wavelength, low energy hitting our metal, and there's no emissions because it hasn't reached the threshold. Here's a little bit more energy, but it must at least be enough to see that the low energy photons are being emitted, but we have even higher energy, and the photons that are being emitted are higher energy.
So concluding this, there's a one-to-one correspondence between ejected electrons and light waves. But it can only occur if light consists of individual units called photons, which is a packet of light that has a certain amount of energy. So what's the gist of it? Demonstrates that light, usually considered to be a wave, can also have the properties of particles, however, without mass. And like we just said, for each metal, there is a threshold wavelength. And cesium, for example, can emit electrons with red light. Some other metals require yellow light or even UV light to emit photons. So let's think about a situation. You're an engineer. You're designing a switch that works via the photoelectric effect. The metal used requires 6.7 times 10 to the negative 19 joules per atom to eject electrons. Will the switch work with light of 540 nanometers or greater? Why or why not? Well, so we need to determine that minimum threshold energy. If that is greater, then the electrons will be ejected. If not, then the switch won't work. So let's think about our equation. The energy of the photon equal to H times V, and we know that V is equal to C over lambda. So we know our H is our Planck's constant. This is a known number times C, 3 times 10 to the 8th meters per second. That is the speed of light. That is also known. And we changed 540 nanometers into meters. We get 3.7 times 10 to the negative 19. This number is less than 6.7. So the energy of the light is below the minimum threshold. So there will not be any ejection of electrons. It needs to have a wavelength of less than or equal to 297 nanometers to eject this. Let's look at another problem. DVD players use lasers that emit red light with a wavelength of 640 nanometers. What is the energy of one photon of this light? So remember that V is equal to the speed of light over wavelength. And we know that E is equal to hV. So I'm going to take what this V equals and plug it into that V. So E is equal to H times C over wavelength. Now we can plug in our Planck's constant, which is 6.626 times 10 to the negative 34th, and that's joules per second. And then we're going to times by the speed of light, so times 3.00 times 10 to the 8th meters per second, all divided by the wavelength, which is 640 nanometers. We know that nanometers is equal to 640 times 10 to the negative 9 meters. So let's see what we get when we do this. plug it into your calculator with me, and I got 3.1 times 10 to the negative 19. Hopefully you got the same. I'm going to write it up here. And let's see what our units are. We've got meters and meters canceling, seconds and seconds canceling, and this should be joules per 1 photon. All right, so that's energy for 1 photon. What's the energy of 1 mole of photon? Well, we know that in 1 mole of anything, there's 6.02 times 10 to the 23rd of particles, atoms, molecules, photons is right in that with that same thing. So since photons is on the bottom here, we're going to just multiply this whole thing by 6.022 times 10 to the 23rd, and this is particles per mole. There we go. So let's see if I take that answer and times 6.022 and 10 to the 23rd, and I get 187,039. So let's make that into scientific notation. How about 1.9 times 10 to the 5th? And that'll be joules per mole of red light. How about you try this one? Calculate the energy per mole of photons for the laser used in Blu-ray players, which the wavelength of Blu-ray player lasers is 405 nanometers. So why don't you try pausing this and seeing if you can set that up. All right, so they plugged in, used the speed of light equation, speed of light is equal to wavelength times frequency. So they calculated V first. We'll get the same answer at the end though if you did it just like the last problem. So we did the speed of light, 2.998. If you use 3.00, we're going to get the same answer. 3.00 times 10 to the 8th times. Now you could have also written this as 405 times 10 to the negative 9. And that's for right here. 405 times 10 to the negative 9. You would get the same thing. And then once they found V, they plugged V into E equals HV. And so again, pretend like this 6.022 isn't there quite yet. So we took our answer here that we got for V and plugged it, times it by H. And then when we got that answer, since we wanted per mole, we times the whole thing by 6.022 times 10 to the 23rd. Given 3 sig figs up here, 295,000 joules per mole. And then you could also simplify that if you wanted to change it to kilojoules, that it would be 295 kilojoules. So either way. Now we know that electromagnetic radiation has wave properties, but we have also seen that there are experiments such as the photoelectric effect for which it's best to model it as particles called photons. So how can electromagnetic radiation be both a particle and a wave? In part, we're facing limitations in language because the word particle and wave accurately describe things encountered on a macroscopic scale. But we're using them to model something, the electromagnetic radiation, that's not fully explained by either term. Additionally, no single experiment has yet to be done to show electromagnetic radiation behaving simultaneously as a wave and a particle. So interestingly enough, scientists now accept this wave-particle duality. That is, the idea that electromagnetic radiation has the properties of both a wave and a particle. So this leads us to our next section, section 3, looking at atomic line spectra and Niels Bohr. So let's say that high voltage is applied to atoms of an element in the gas phase at low pressure. These atoms absorb energy and are said to be excited. The excited atoms can then emit light when they fall from the higher energy to a lower energy. A familiar example of this is the colored light from neon signs. And we saw all different colors of neon lights, even though only one of them is actually neon and the rest are other noble gases.
We can demonstrate this by passing a beam of light from excited neon or hydrogen atoms through a prism. Only a few colored lines are seen. This is called our emission spectra. Excited atoms emit light of only certain wavelengths, and the wavelengths of emitted light are unique to each individual element. We can see here that we have our excited gas giving off, let's say this is our hydrogen, and it's giving off this glow. It goes through this beam of light, through the prism, and the wavelengths that are observed in the visible range are unique for that specific element. For example, here's some line spectra for hydrogen, for mercury, and for neon. And as you can see, Each element has a unique emission spectra. This can be used for chemical analysis to identify the element and to see how much of it there is present. And the emission spectra for each element is like its fingerprint. As you can see here, how many bands of color you see and where they are in the spectrum. As you can see, there's many different wavelengths of red light, so you can see where those are.
Here is one view of atomic structure from early in the 20th century, showing us that electrons they move about in orbit. Well, Bohr said that line spectra of elements indicated the electrons were confined to specific energy states, called these orbits, and that they are quantized, so there are only certain levels allowed. He also said that the line spectra indicated that electrons were jumping or transitioning between energy levels. So this is showing us that we would see red if an electron jumped up to this energy level and then fell back down only one. We would see a certain color. Here would be an example if an electron jumped 2 orbits and fell back down, we would see a certain color, and so on. So back early in the 20th century, the Danish physicist Niels Bohr proposed a model for the electronic structure of atoms, and with it, an explanation for the emission spectra of excited atoms. Bohr proposed a planetary structure for the hydrogen atom, in which the electron moved in a circular orbit around the nucleus, similar to a planet revolving around the sun, like those last pictures. In proposing this model, however, he had to contradict the law of classical physics. Because according to classical theories, a charged electron moving in the positive electric field of the nucleus should lose energy. A consequence of the loss of energy is that the electron would eventually crash into the nucleus. Well, this is clearly not the case. If it were, matter would eventually self-destruct. To solve this contradiction, Bohr postulated that there are certain orbits corresponding to particular energy levels where this would not occur. As long as an electron occupies one of these energy levels, the system is stable. That is, Bohr introduced quantization into the description of electronic structure. By combining this quantization postulate with Coulomb's law and the law of motion from classical physics, Bohr derived an equation for the total energy possessed by a single electron in the nth orbital or nth energy level of a hydrogen atom. We're going to look at that here. This is able to tell us the energy of an electron in the nth level, En, is equal to Rydberg constant times Planck's constant times the speed of light, all divided by the principal quantum number squared. Now remember, our n is equal to 1 is located in the orbit that's closest to the nucleus and has the lowest or most negative energy. And as the value of n increases, the distance of the electron from the nucleus increases, and the energy of the electron becomes higher or less negative. So when an atom with its electrons in the lowest possible energy level is in its ground state, then the level defined by the quantum number is n equals 1. And then when it is at an excited state, that means that n is greater than 1, so it has higher energy. And this just kind of shows us an example for hydrogen. This is when n equals 1, so this is my first orbital, my ground state, and then we can see the energy associated with the electron at the ground state, and then energy when n equals 2, and then the energy when n equals 3. And we can see that the difference between these successive energy levels becomes smaller as n gets larger. All right, let's look at a couple questions. Let's say that we're looking at a hydrogen atom, so 1 electron. Assume the emission spectra of an excited hydrogen atom will consist of transitions only between these levels. How many emission lines are possible considering only the 5 quantum levels shown? So we're given 5 different quantum levels. How many different transitions can one electron do? Well, what if we went from 5 all the way down to 1. That would be 1 transition. About 5 down to 2. That would be 2. 5 to 3 would be 3. 5 to 4 would be 4. What if my electron started at 4? 4 down to 3 would be 5. 4 down to 2 would be 6. 4 down to 1 would be 7. What if I started at 3? 3 to 2, that would be 8. 3 to 1 would be 9. And then I could go from just 2 to 1. So I could have 10 total transitions. How about this one? Consider only the quantum levels below for the hydrogen atom. Photons of the highest frequency will be emitted in a transition from the level of blank to the level blank. What do you think? The highest frequency. What do you think? Hopefully you said 5 to 1. That's the greatest difference. What about this one? Which emission line would have the longest wavelength? Transitioning from where to where, looking at this problem. The longest wavelength. What do you think? Well, we said in that last question that going from 5 to 1 was the greatest frequency. Highest frequency. The longest wavelength, though, so the greater the frequency, the shorter the wavelength. So the longer the wavelength would be the complete opposite, which is the shortest transition should be from 5 to 4. Think about longest wavelength would be the shortest or the smallest frequency. So let's go back and think about that equation, that E equals negative RHC that we just were looking at before we did those questions. This equation. Think about this equation. Calculate the energies of N equals 1 and N equals 2 states of the hydrogen atom in joules per atom and in kilojoules per mole. What is the difference in energy of these two states in kilojoules per mole? So think about what we know, that N1 and N equals 2 are the first and second states, the lowest, and the next to the lowest energy state in the Bohr description of the hydrogen atom. So we're going to use that equation from up above to determine the energy of each state. Remember, we do know R, Rydberg's constant is given right here. We know H, Planck's constant, and we know the speed of light right here. We also know Avogadro's number. This is how many atoms there are in a mole. See if you can set up this problem. Take a minute. All right, let's check your answers. So let's look at when N is 1. So again, we're going to use negative RHC. So here's our negative R, we've got H, we've got C, and we just need to multiply these 3 together, and we get negative 2.179 times 10 to the negative 18th joules per atom. Now, to turn that into kilojoules per mole, we took our joules per atom answer. I got to have atoms on top. And we know that there's 6.022 times 10 to the 23rd atoms in 1 mole. And then to get rid of joules, I had to have joules on the bottom over here. 1,000 joules and 1 kilojoule. So I would get negative 1,312 kilojoules per mole. Now, when I have 2, when N is equal to 2, I am able to, I've got to look back at this equation. When it was 1, 1 squared is just 1. So having that whole equation divided by 1 is equal to having that equation just by itself right here. But having it at second energy level, notice that I had to do my negative RHC over 2 squared. So I'm going to take the answer that I got from up here, because that's the top number, and then divide it by 4. So I should get negative 5.448 times 10 to the negative 19th joules per atom. And again, I'm going to change that into kilojoules per mole using the same conversion factors as I did. I got to have joules on the bottom and atoms on the top. So then to find the difference, I'm just going to take my second energy minus my first energy to get my difference. And I should get 984 kilojoules per mole. All right, let's do one more practice and calculate the energy of the N equals 3 state of the hydrogen atom in joules per atom and kilojoules per mole. Pause this and then try to get your own answer. All right, let's check your answer. Did you do negative RHC divided by 3 squared, so divided by 9, to get negative 2.4211 times 10 to the negative 19th joules per atom? And then to find per mole, we took our answer and times it by 6.022 times 10 to the 23rd and divided by 1,000 to get negative 145.8 kilojoules per mole. Here is a nice summary of this section that kind of wraps up everything.
At the beginning of the 20th century, the model of the atom was that it was a ball of positive protons and negative electrons, a model that did not begin to explain a number of fundamental observations. But just at the beginning of the century, experiments by J.J. Thomson and Ernest Rutherford in England found that the atom in fact consisted of a dense nucleus of protons with electrons around that nucleus. It was Niels Bohr who finally put these ideas together with other experimental information to fashion the theory of atomic structure that we use today. A puzzling property of elements was that when excited they emitted light, not in a continuous spectrum, but as discrete wavelengths. And each element was different. Here you see spectra for hydrogen, mercury, and neon, and each element emits light of different wavelengths. In the late 19th century, Johann Balmer and Johannes Rydberg studied emission spectra of the elements, and for hydrogen they found that the wavelengths of the light could be calculated using a simple equation. But why does this work? Why is there a simple equation governing what is clearly more complicated behavior? Bohr's theory provided an explanation for the emission spectra of the elements and was the beginning of a theoretical understanding of the experimental Balmer equation. In the Bohr model of the atom, electrons exist in circular orbits around the nucleus. A key idea of the model is that only certain orbits of particular energies are allowed. As long as the electron occupies one of these orbits, the system is stable. Importantly, this introduced the idea of quantization, that electrons cannot have random energies, but only certain energies in a stable system. Bohr derived the equation for the energy of an electron in an orbit. This equation states that the energy depends on three constants: the Rydberg constant, Planck's constant, and the speed of light, and inversely on the square of the principal quantum number, n. The principal quantum number, n, can have only certain values, integer values, that is 1, 2, 3, and so on. And this is the reason we say that energy in the atom is quantized. Let's think about this some more. I think of the electron in an atom as being at the bottom of an energy well. If n equals 1, it is at the very bottom of the well, because 1 squared is 1. The energy of the electron in this state is simply equal to minus RHC. But if n equals 2, then it is at an energy of minus RHC divided by 4, or only 1/4 of the way to the bottom of the energy well. If n equals 3, then it is only 1/9 of the way to the bottom of the well, and so on. Now, with this picture in mind, let's do some energy calculations. We want to calculate the energies of the n equals 1 and n equals 2 states for the hydrogen atom. As usual, we ask what to...
And we already did this, so I'm just going to
number.
skip forward here.
n equals 1, the energy is minus... What is the energy difference between the n equals 1 and n equals 2 levels? It is 984 kilojoules per mole. What this means is that to move an electron from n equals 1 to n equals 2 in a mole of hydrogen atoms, 984 kilojoules per mole are required. If the electron returns to the n equals 1 level, then 984 kilojoules are emitted. This is the key to thinking about the spectra of atoms, as you will see in more examples in this section of the book.
Now, Bohr's theory describes electrons as having only specific orbits and energies. So if an electron moves from one energy level to another, then energy must be absorbed. This idea allowed Bohr to relate energies of electrons and the emission spectrum of hydrogen atoms. So to move an electron from N1 state to an excited state, so going from N1 right here up to N2, energy must be transferred to the atom from the surroundings. So our E final, so to find out this energy, we need to do final minus initial. Just like if we're doing the delta T is T final temperature minus initial temperature. To find out this delta E, we need to do our energy of N at N equals 2. That would be our final. and then the energy at n equals 1, which would be our initial, and then we would subtract the 2. So we just did that negative RHC over n squared. So in this case, we can see that the difference, if we do final minus initial, is going up. That means energy is absorbed, and we have a positive delta E. In this case, it happens to be 984 kilojoules per mole. That must be transferred. No more, no less. Now, it's now at an excited state. For it to go back down to the ground state is the opposite process. So the electron is falling, quote unquote, from a level of higher n to one of a lower n. So this is an emission of energy, a transfer of energy. And it's usually as radiation from the atom to its surroundings. So if I were to do this to find this delta E, I need to do final, which would be N1, minus the initial E, which would be at 2. So to do final minus initial, using the same numbers, just using them in opposite way, we get a negative delta E. So negative 984 kilojoules per mole, which means energy is emitted. The positive sign tells us the energy is absorbed. The negative sign tells us the energy is emitted. Now, depending on how much energy is added, some atoms have their electrons excited from the N1 state to the N2, 3, or even higher states. After absorbing energy, these electrons can return to any lower level, either directly or in a series of steps. And when it does that, it releases energy. So we can see we observe this released energy as photons of electromagnetic radiation. Because only certain energy levels are possible, only photons with particular energies and wavelengths are emitted. So if we were to look at this, we can see an electron is excited to N3, can return directly down to N1, and we would find that delta E by doing final minus initial, or here we can see the change in, it should be 1 minus 3, or we can see that we can go in a series of steps. So first it went from N3 to N2, and we could see that it released this electromagnetic radiation, and then it can then fall from 2 to 1. So far we've covered these two equations, and we've talked about finding delta E is the E final, so taking this minus initial, which would then look like this. I would take, to find 1E, this is 1, so it would be final minus initial E. But we can simplify this and pull out negative RHC and times it by the difference of 1 over the final energy level, or N, final N minus initial N, to get this. So we can find this if we know the N's that we are going from and to. It's also important to note that the value of delta E, which is in joules per atoms, can be related to the wavelength or frequency of radiation using Planck's constant. We talked about using Planck's constant earlier, so we can use that energy to find the wavelength of the light that's being emitted. And to do that, we would take the absolute value. So if we had a negative E, right, like if it is emitting light, we would just take the absolute value of it. So we would use the positive value of that number to just make sure that we have a positive wavelength, because there is no such thing as having the negative wavelength. And so we could rearrange that equation to find the wavelength of a photon by doing h times Planck's constant times the speed of light all over the absolute value of E that we found. So here's a for example problem. If we wanted to determine the photon wavelength of a transition between two energy levels, let's say the energy levels were second energy level to the fifth energy level. So we're going from N2 up to 2,5. So it is absorbing energy. So again, I can use that equation, negative RHC, which all multiplied together is negative 2.179 times 10 to the negative 18th joules, times, and then we would take our N final, so 1 over 5 squared minus 1 over 2 squared. And then we would find that our delta E was 4.576 times 10 to the negative 19th joules. And E is positive because it is absorbing energy. Be careful and don't try to cheat, because 1 over n squared minus 1 over n squared, the final minus initial, is not equal to saying 1 over n squared minus n squared. Don't do that. For example, if we took that 5 and 2 from earlier, 1 over 5 squared is 25, 1 over 2 squared is 4th. So 1/25 minus 1/4 is equal to this, negative 0.21, and this, if I were to do it, is equal to positive 0.048. So we get different answers. Make sure that you stick with the way that the equation is written. So if we were to go one step further, because we need to find the wavelength, we're going to take that E that we calculated from the page before. I'm going to flip back here real quick. Here we go. This E that we found is 4.576 times 10 to the negative 19. We're going to use that equal to H, constant, times C, speed of light, or I guess all divided by my E, using this equation from the slide before. So the wavelength of the photon, all right, that's going to cancel out my joules and joules, seconds and seconds, and I'm left with meters. We do that and we get 4.340 times 10 to the negative 7th meters. And to convert that into nanometers, again, there's 10 to the 9th nanometers and 1 meter. So we should get a wavelength of 434 nanometers. All right, let's do another practice problem to wrap up this lesson. I want to calculate the wavelength of the green line in the visible spectrum of excited hydrogen atoms. So we need to look at this figure. This was 610. So here's our green line, and we got this green line, if I follow it back, from hydrogen atoms going from N4 to N2. Okay, so knowing that information, calculate the wavelength of the green line that we know that it went from N4 to N2. Why don't you pause this and try your work? We'll go over it in a second. All right, let's see how you did. So to find our delta E, we're going to do E final minus E initial. And since we have two different N's, we can abbreviate. We can do negative RHC, and then in parentheses, our final was our second N level. The initial was 4. So we know negative RHC times 1 over 2 times 2 is 4. 1/4 minus 1/16 to get 0.1875 times that negative RHC. And we should get negative 4.0859 times 10 to the negative 19th joules per photon. Now we know that it's negative. We are falling. We are emitting light. Now to find that wavelength, we can plug it into our equation. Hc divided by E. So H, Planck's constant, times the speed of light divided by what we just found. But remember, it's got to be the absolute value of what we found. And we would get meters. Meters to nanometers, because there's 10 to the 9th nanometers in 1 meter. You should get 486.2 nanometers. And if we go back to look at this green line that we see, 486.1 nanometers, so it's pretty darn close. So Bohr's model, introducing quantization into a description of the atom, tied together the unseen, so the structure of the atom, to the seen, the observable lines in the hydrogen spectrum. This is important because agreement between theory and experiment is taken as evidence that the theoretical model is valid. However, the theory was imperfect. This model of the atom explained only the spectrum of hydrogen atoms and other systems having 1 electron, like helium with a +1 charge. But it failed for all other systems. So a better model of electronic structure was needed, and we'll talk about that next. But first, let's do one more practice problem. Calculate the energy of the photon of light emitted when an electron in a hydrogen atom undergoes a transition from N4 to N3. So just this, what will we see, what energy? So pause it, do your calculation, and we will check our answer. And hopefully you got this one.